So the last part of chapter 10 here talks about the physical properties of these alkanes, and this holds true whether they're cycloalkanes or the acyclic linear alkanes. And the reason it doesn't matter is because both of them only contain carbon-carbon and carbon-hydrogen bonds, both of which are nonpolar. So the fact that these molecules are nonpolar means they're going to have physical properties characteristic of nonpolar molecules, which you guys should be familiar with back on, if you think back to what we talked about in chapter 3, and that is to say that alkanes and in general nonpolar molecules typically have weak intermolecular forces, right? And because of that, they're also going to have lower boiling points and melting points, right? There's not as many forces holding them together, so it's easier to pull them apart, so it takes less energy or less heat to melt them or boil them. Smaller alkanes are going to be gases at room temperature. Larger ones are going to be liquids. And usually that transitions somewhere around butane. Like if you think of a butane lighter, that usually has some liquid in there, whereas a propane gas, that's like gas tank that you would use like for a grill or something like that. That's actually gas. Alkanes are going to be insoluble in water. Remember, like dissolves like. Water is polar, these are nonpolar, so they're not compatible. So alkanes are going to be insoluble in water. And they're also less dense in water, meaning if you put the two together, they're not going to, not only will they not mix, but the alkanes will float on top of the water. The water is going to be more dense and go to the bottom. Mentioned before that as the number of carbons increases, they're more likely to be liquids. That's the same thing that this slide is showing, where you have more carbons, the boiling point increases. So butane, pentane, and hexane. If you look here, it's actually showing is butane as a boiling point of negative 0.5 degrees, which means at room temperature, like 20 degrees Celsius, it would actually be a gas. That's because those butane lighters that we just talked about are actually not pure butane. They're kind of well, this actually is a bit like isobutane and has some other stuff in there to make it so it's liquid, but it's also very flammable. And we'll talk about the flammable nature of these things in just a minute. Well, we'll talk about them right now, I guess, because, right, so natural gas and other gases are comprised primarily of these types of alkanes. So natural gas is going to be mainly methane. Methane burns in the presence of oxygen and it releases heat, right? We use that to cook, we use that to heat homes and things like that. Petroleum is a mixture of compounds that can be refined, but whenever you do that petroleum refinement, you break it down into various alkanes, which can be used to things like gasoline, kerosene, and diesel fuel. All of these are going to be alkanes of different length. Like if you look at gasoline, it's like C5H12 to C12H26. Well, typically, like if you look at gasoline, one of the primary components in there is octane, which would be, right, octane would be C8H18, which would be right in the middle there for gas. And then other portions of that petroleum refinement can be used to make plastic, drugs, fabrics, other stuff like that. Okay, so as we talk and go through our sections on organic chemistry, we're going to look at different reactions that different types of molecules have. Alkanes in general go through very few reactions, and the only real reaction that you need to know for alkanes is a combustion reaction. It's also the type of redox or an oxidation reaction. And basically this reaction says that alkanes burn in the presence of oxygen. In other words, they react with oxygen to form CO2 and H2O, right? So that's going to be a combustion reaction. And the trick here to these is you have to figure out what your alkane is, and you don't write it as alkane, you would write it as like C4H10 or something like that. And then you would need to go through and balance that equation. And we'll do a couple practice problems on this here in just a second. So regardless of what is what your starting material is. Like in this case, it shows isooctane, which is the high octane component of gas, right? The products are always going to be CO2 and H2O. In other words, you're always going to end up with carbon dioxide, water, and a great deal of energy comes off of that as well, and that's that energy we use to heat things. Whoops. Now, there are times when you might not have enough oxygen to undergo a complete reaction. And in those cases, we have what is referred to as incomplete combustion occurring. So that you can think of this as like the second reaction you need to know. And the only difference in incomplete combustion is going to be the formation of CO instead of CO2. You make carbon monoxide instead of carbon dioxide. So in incomplete combustion, you get carbon monoxide. And carbon monoxide is a poisonous gas. So it works, basically it binds to hemoglobin, and hemoglobin is important for carrying oxygen around through your blood. We'll actually talk about hemoglobin once we get to the biochemistry part of the course. But carbon monoxide binds to the hemoglobin a lot better than regular oxygen does. So carbon monoxide binds, it prevents the oxygen from binding to it, and that way the hemoglobin carries around carbon monoxide. It doesn't let go of it, and those tissues that are hungry for oxygen end up basically becoming oxygen starved, and they die, and as a result, you can die, which is why this is a very poisonous gas. Okay, so the last thing we're going to do here is a couple practice problems on writing these combustion reactions. So the first one says write the balanced reaction for 2-methylbutane. So if you get something like this, the first thing you need to do is write out what 2-methylbutane is. So butane is 4 carbons, and then 2-methyl means on carbon 2 we're going to have a CH3 there. So I wrote it as a skeletal structure, but I'm also going to come down here and write it as a complete structure. So you're going to have CH3, right? That's a CH3. Right there, you would have a CH with a CH3 above it. Then you're going to have a CH2 and a CH3. Right? That's going to be your CH2, and that's going to be another CH3. So taking a look at that complete structure here, right, we can actually count and write a chemical formula for what this is. So if we count, it's going to have 5 carbons, C5, and if we count all the hydrogens, it's going to be H12. Now, you could go through and count all the hydrogens, or you can remember the formula of CnH2n plus 2. And that would also get you there. You take find out that there's 5 carbons, then you multiply it by 2 and add 2 more. So 5 times 2 is 10, add 2 more, it gets you to H12. Now that you know the formula, we can write the equation. So it reacts with oxygen to form CO2 plus H2O. So now to balance this, whenever you're doing a combustion reaction, in general, it doesn't matter how you balance equations, but for combustion reactions, I tend to do it the same way all the time, which is to balance the carbons first. So now we have 5 and 5. Then we're going to balance the hydrogens, which gives us a 6 here to give us 12 on each side. And now if we count up the oxygens on the right side of the equation, we'd see that we have 10 from there plus another 6 from there, so that's going to be 16 total. So that means we put an 8 there, and that's going to be our balanced equation. Sometimes when you do a combustion reaction, you'll do this, and this ends up being an odd number. That one there ends up being odd. If that's odd, you're not going to be able to put anything there that's going to exactly balance your equation. See if I can think of one off the top of my head. This should work. C4H10. Let me erase to give myself a little more room here. So let's say we were just doing this as, so 2-methylbutane now, let's just do butane. All right, so butane would be C4H10 plus O2 goes to CO2 plus H2O. So again, balance the carbons first. That's 4 on each side, and we have 10 hydrogens on the left. We have 5 times 2 gives us 10 hydrogens on the right. Now if we add up our oxygens, we're going to have 8 from that part, 5 from that part, and we're going to have 13 total oxygens. So that gives us to a problem, because if we were to add 6 over here, we would have 12, and if we add 7, we would have 14. So the problem is we need something right in between. So in a perfect world, we would add 6.5, but we know we can't write a fraction or a decimal to balance an equation. But if you can think of that as 6.5, it's really easy to fix this, because what you're going to do is basically take that whole equation and rewrite it, multiplying everything by 2. So we're going to put coefficients of 2 in front of C4H10 plus, instead of 6.5, we're going to put 6.5 times 2, we would have 13 oxygens plus 8 CO2s plus 10 H2Os. And that would be your answer if it was just butane. Now, if you have a problem figuring out what it would be, that 6.5 number, what I'll tell you to do is, if you have an odd number here, whenever you go to calculate your total number of oxygens, just go ahead and put a 2 in front of your starting alkane and rebalance it, and you'll get to the right answer. Okay? All right, so now let's finish up by doing this one on the bottom here where it says write the balanced incomplete combustion. So that means we're going to form carbon monoxide instead of carbon dioxide for cyclobutane. So cyclobutane is going to be a ring. 4 members is going to be a square, right? And that is going to be C4H8, right? 4 carbons, 8 hydrogens, plus O2 reacts to form not CO2, but just CO plus H2O. Follow the same pattern as before. Balance your carbons first. So we're going to put a 4 over there. Balance the hydrogens next. We have 8 on the left, so we need to put a 4 in front of water. That gives us 8 on the right. Now we add up our total amount of oxygens. We're going to have 4 in CO, and we're going to have 4 in water, so it's going to give us 8 total. We put a 4 there, and that's our final answer.